Hello, I would like to present to you our study and our project, which is Interpretable Multi-modelling of Potato Blight Disease Detection with Retrieval Augmentation Generation. And we are group CS25-10. So these are the contents of our presentation. We shall introduce and talk about our problem statement, our related works, research questions and objectives, research contributions, the methodology, describe our data set, the experimental results, and then conclusions. So my name is Businge Martin William. Allow me to introduce to you our study. So plant diseases, as we all know, pose a significant threat to global food security, with blight diseases being among the most destructive for crops like potatoes. Yeah, agriculture is very important, as we all know, because it provides food. So without agriculture, then we do not have food security. So these blight diseases are a challenge that affect potatoes, and they can drastically reduce the yield and profitability for the farmers. Early blight and late blight particularly are challenging to manage because they propagate quickly and they are difficult to predict early in the field, especially in different environmental conditions. So recent advancements in computer vision and deep learning have provided a promising approach for real-time disease detection, enabling farmers to make informed decisions and reduce crop losses. This is what we look to explore. So in this study, we're going to integrate the power of computer vision, which we're going to combine with Retrieval Augmented Generation, RAG, to develop an advanced system which will detect and manage the blight diseases in potatoes. So let's look at our problem statement. Potato blight is caused by Phytophthora infestans and poses a serious threat to potato crops worldwide. It results into significant yield losses and economic hardships, and of course, not forgetting that it also risks the food security situation. So managing this disease efficiently requires early detection and accurate diagnosis. However, the traditional methods that exist, they are slow, they require a lot of labor, and they rely on an expert's knowledge, meaning that they require an expert to be present. So some farmers operate in resource-limited regions, and these struggle to access timely and reliable information on the disease symptoms, treatment, and the prevention strategies. This is where our project comes in, because our project is going to address these three challenges by developing an integrated system that combines computer vision for automated detection of the potato blight disease, be it early or late blight, and it's going to combine it with Retrieval Augmented Generation application for providing the recommendations. So a farmer can upload the image of the potato and they receive instant disease detection results. And also they can access actionable advice for treatment and prevention. So the primary challenges we are trying to overcome in our project's development are: we want to achieve high detection accuracy so that the model detects that the disease is this and it is that, even under different conditions. For example, maybe rainy conditions, some areas have too much sunshine. We want to ensure low latency for real-time results. The model should be able to detect the disease as soonest as possible and give the results very soon. And also, we want to integrate computer vision with knowledge retrieval, which is a bit challenging, but it's what we want to achieve. So our goal is to deliver a user-friendly and a scalable tool that empowers farmers to manage potato blight more efficiently, reduce crop losses, and improve productivity. So our computational problems, there are two main problems. The first one being multimodal data fusion, which means that we want to fuse data from different formats and from different sources to be able to work together. Take, for example, we use image data for the model, and then we use text data for the RAG component. So we want these two to be able to work together in our model. And then secondly, the black box nature and the model explainability. Of course, most of these models that we use, we do not know how they work. So another computation problem that we want to solve is that we want to be able to understand the functionality of this model and be able to know what it bases on, which areas it places focus on, and what is most significant to this model when it is making the predictions. It is making the different predictions and what it bases on to determine that the disease is this or that, maybe early blight or late blight, or maybe that the crop is healthy and then makes the predictions. The recommendations.
Hi everyone. My name is Namakula Josephine, and I'm going to start from where my colleague is from our project, which is called Interpretable Multi-modelling of Potato Blight Disease Detection with Retrieval Augmentation Generation. So first of all, I'm going to first pass through what we have done so far. First of all, we got our second data set. It had 6 classes: late blight, early blight, healthy, virus, fungi, and other pests and pests. So we considered only 3 classes, which is late blight, early blight, and healthy. We carried out exploited data analysis. We built 7 models. We chose the best one out of them after adding interpretability on them. Then after we built our RAG, where we scrapped about 21 PDFs from 21 PDFs, which are relating to potato blight, disease detections and prevention. We carried out exploited data analysis on it. We built our RAG system. Then after, we fused our RAG system with our best model. So we used we also employed ChatGPT API. So I'm starting with related works. The paper is called Detection of Potato Disease using artificial intelligence. The limitations, they had the variable lighting and shadows, inference time variability, class-specific accuracy challenges. The second paper is early blight and late blight disease detection using potato, using efficient bin note. The third paper is investigating potato late blight psychological differences across potato cultivars with spectroscopy and machine learning. So when I move to the next slide, I find our research objectives and questions. So the main objective, it was to develop an AI-driven system combining computer vision and retrieval augmented generation for effective detection and management of late blight and early blight in potatoes and tomatoes. So to identify our other research objectives, we had to identify and create data sets suitable for training computer vision models to train early and late blight, to develop a computer vision model capable of accurately diagnosing blight from crop images, to integrate a retrieval augmented generation system for personalized context-aware advisory services, also to evaluate the effectiveness and usability of the combined computer vision and drug system for real-world agriculture applications. When I move to the next slide, I find the research contributions, like what we did. We developed a multimodal AI system for potato blight disease detection and diagnosis. As I said, the system, when you upload an image, it detects whether the plant is diseased, late blight or early blight. So it gives you the confidence interval. Then the model itself explains its results. Then after, it sends the results to the GPT-4. Then the GPT-4 provides the personalized advice and prevention mechanisms. So we evaluated and compared 7 deep learning models for disease classifications. We integrated GPT-4-powered drug module for context-aware recommendations. We applied explainable AI tools to improve model interpretability. We have also delivered a scalable, interpretable, and user-friendly system for precision agriculture. When I move to the next slide, I find our research methodology. First of all, as I said, we gathered raw data from the uh, from our sources, as my colleague has said, the late blight and early blight image data. We carried out exploited data analysis, data selection, and pre-processing. We split the data into tested data, validation data, and trained data. We evaluated the model. We carried out explainable AI on those models because we didn't know what they were actually meaning. Then after our model, we combined the two, model and the RAG applications into one. That's called multi-modeling, and also we carried out validation and user testing. Then after, we deployed our system
using an existing data set from IEEE Dataport, which was released in December of 2024 on the 26th, and it contained 6,748 labeled potato leaves across 6 categories. And these categories were, we have healthy leaves, we have those infected by early blight, late blight, we have those which were attacked by pests, then we have those affected by virus and fungi. But for the sake of our model, we only focused on 3, which are relevant, which is early blight, late blight, and the healthy ones. And for the RAG component, we collected 31 PDFs from different sources, and these included Google Scholar and the Ministry of Agriculture, Animal Industry, and Fisheries. And then we scrapped them using Python, and we compiled them into a text corpus, which we stored in the text format so that it can be easily processed by our model. So we tested several deep learning models, to classify the leaf images. So the table you see here is comparing their performance using the metrics of loss and accuracy on both training and validation data. In our situation, accuracy is referring to the percentage of prediction the model got correct out of all the predictions. In simple terms, it's telling us how often the model is right. And then loss is referring to how far off the model's predictions were from the actual labels, or in simple terms, it's telling us how far off it is when it is wrong. So from this table, we can observe that DenseNet 121 and Inception v3 have the highest accuracy and the lowest loss for both the training data and the validation data. And EfficientNet B0 and Vision Transformer have the highest loss and the lowest accuracy for both sets of data. Therefore, we can conclude that DenseNet 121 and Inception v3 were excellent in the prediction performance for both training and validation, and EfficientNet B0 and Vision Transformer have poor accuracy and high loss, so maybe they were not suitable for their function. We take one example of DenseNet 121. You can see that its loss is 0.1249, but that is about 12%, 12.49%, and its accuracy is 0.534, which is about 95.34%. That is for the training data. And when you look at the validation data, its accuracy is 0.9533, which is close to 95.33%, which is almost identical to the accuracy on the training data. So you can see that, yeah, it is fitted well for our training. Then here, we look at 2 very important images. One is one being the box plot, and the other one is the word cloud. These are both very important in explaining our different data sets. The box plot focusing mostly on the image data, and the word cloud focusing on the text that we're using for the RAG component. So in our box plot, we're just visualizing the distribution of pixel intensity values for each class of the potato leaves. That is for all the different 6 categories which were in our original data set. As you can see, early blight, fungi, healthy, late blight, pests, and virus. So each box is showing the interquartile range, that is the middle 50 of the pixel values. And the line inside the box of each value is the median value. So as you can see here, early blight, which is the first one towards the left, has relatively high median high median brightness. And late blight, which is the fourth from the left, tends to be dark with a low median. And then the ones which are healthy fall somewhere in the middle. Those are the ones we're focusing on mostly for our study, because they're the ones relevant to us. And this is showing us that these different disease types are manifesting visually in different ways. Therefore, image-based classification is possible. And then when you look at the word cloud, it's just basically a visual summary of the most common terms in the document, which we are using for the RAG component. So the larger the word, the more frequently it appears. So we generated it from the 31 PDFs that we collected from our different sources, as mentioned earlier. So as you can see, large words like plant, late blight, soil, affect, solid, yields, disease, these are the core themes in our literature. So we can confirm that our text data is highly relevant to the potato blight problem, which is crucial for our RAG system. And as you can see from here, the literature is focusing on the words which our image classification model is trying to detect visually. So our RAG component and our image classification models are working hand in hand. Then we also look at this image, which is trying to bring a bit of explainability with how our model works. So we have an original image to the farthest left, and then we have this image here, which is the second image from the right, which is the output of the local interpretable model agnostic explanations method, commonly abbreviated as LIME. So it is helping us to understand the parts which the model is using mostly for the prediction. If you see the yellow lines, the yellow curves are highlighting the parts which are mostly based on. Now, this image that we have, the original image, is an image of a leaf affected by early blight, and is characterized by dark spots. When you look at the second image, you can see that the dark spots are the ones which are highlighted, which is showing that our model is indeed focusing on the right parts in its prediction. And then to the furthermost right, we are using gradient weighted class activation mapping, which is a GradCam, to show the points of focus. We have gradients ranging from blue to red, with red showing the most significant ones. So when you look at our original image once again, and you look at the GradCam image, you can see that the red part is the part which has the dots. And that shows that our image is indeed focusing on the right parts to make its what? To make its predictions. So therefore, this again shows us that, yeah, our image is using the most affected parts to make its prediction. And this is going to help us to understand more what it bases on to make its predictions and to maybe trust its results more.
Yes, hello, I'm Tomasli Ibrahim, and I'm going to take you through this part of the presentation. So this is our system, and we begin by the user logging in, which completes the activity of user authentication into the system. And upon step 2, which is authentication successful, and the user goes to step 3, which is image upload or text. So upon successful authentication, the user is capable of uploading an image or writing a text to the model, which is then analyzed. So the model bases on the image which is analyzed, which is given, and then analyzes it, and then based on the image and all the text that is given, so the model is capable of predicting, giving and then giving a diagnosis, and also giving the disease class. So the RAG module that is into the system gives recommendations based on the predictions of the disease and the diagnosis. Then this is the outlook of the front end of the system. So the system has features of disease classification, treatment recommendations, and expert knowledge. So based on the two features, the text and image, the user is capable of writing a text and uploading the image of the crop.